Alright, hello everybody, this is Dr. Pennington again. I want to talk to you guys today about something called lattice energy. Lattice energy is a useful thing for us to talk about before we get into any real discussion of Lewis structures and how molecules are put together, atoms put together in molecules. Lewis structures primarily deal with covalent compounds, in other words, those that have covalent bonds. Lattice energy tends to deal with compounds that are comprised of ions, or obviously ionic compounds. And if we just think about what the term lattice energy actually means, it's kind of a somewhat abstract concept, but it does help us understand what's actually happening. You can actually take solid sodium, and you can see videos of this on YouTube. It's actually kind of a cool thing to see. Solid sodium metal, and you guys remember how reactive that is, what it does with water. You guys saw that. React it with chlorine gas. You guys also know chlorine gas is not nice. Chlorine gas was the very first example of a gaseous chemical warfare agent. So you can go from two things that are nasty to something that not only is not nasty at all, but it's actually necessary in the human body. So sodium on the one hand is nasty, and sodium on the other hand it's not. So what's the difference? Well, of course the difference is this is Na plus and this is Cl minus. Na plus is not the same as Na. We've seen this in class before. The electron configurations are different, the reactivities are completely different. This is stable, this is not. Same as chlorine. The chlorine wants one more valence electron, the chloride already has it, so it's stable. Anyway, from a theoretical standpoint, the lattice energy is the bringing together of two gaseous ions to form a solid. Now, in reality, it doesn't really work that way. We have the solid sodium here, the gaseous chlorine here. We bring them together, we heat them up, and then we have an exothermic reaction. We get out the solid. But from a theoretical point of view, you bring these together, and notice it says heat is emitted here. Now, what that means is originally these guys are unstable, which is what you could say here. The product we have here is very stable, so there's a net big difference of energy, and that's got to be released somehow, and that comes out in the form of heat, or sometimes light if it's particularly exothermic. And you can imagine that because we have positive sodium ions and negative chloride ions, there is a big attraction here between these guys. That's why they orient themselves in the highly ordered structure that they do, and why this structure is so stable. Alright? This is almost like the way you would build a brick wall. You would not build a brick wall with bricks stacked directly on top of each other. Okay, those are pretty crappy looking bricks. What you would do is you would stagger them to build for a more stable foundation. Okay, that looks awful, dude. There's a reason I did not become I'm not even sure what the word is. Anything to do with drawing whatsoever. Anyway, so you want to kind of stagger them, and that's exactly what's happening here. So very, very stable compound here. That's why table salt is as stable as it is. Anyway, so the lattice energy is the energy involved in the formation of the elements to give the ionic compound. And it's always exothermic. Now, exothermic, what does that mean? Exothermic means energy is released. Exo meaning out, energy comes out. Just as in exoskeleton. Exoskeleton is on the outside. Like Sigourney Weaver wore in the movie Aliens. She had an exoskeleton where she fought the Queen Alien, for those nerdy types of you who know what I'm talking about. Did I say alien or aliens? Anyway, whatever, it doesn't matter. And notice the exothermic nature of this lattice energy is indicated by the negative sign, meaning there is less energy here than there was at the beginning, so energy came out. But notice that there is that not all ionic compounds have exactly the same lattice energy. If I was to bring together lithium and chlorine, I get a bunch of energy out, a negative 834 kilojoules. Now the negative means 834 kilojoules per mole come out. It doesn't mean negative that number comes out, because you can't have a negative energy. A negative just talks about the sign that the energy is moving in. Sodium chloride, you have a little bit less energy given out, and then when we get down to cesium chloride, then the energy is even less. So what's the difference here? Because all we're doing is bringing two atoms together, one metal, one non-metal. Well, actually, the difference here is due to the one variable here, which is the size of the metal. Because you can see the size of the chlorine, of course, doesn't change. Lithium's the smallest, sodium's the next biggest, potassium is the next biggest, and then cesium's the biggest. Notice the charge in each case is exactly the same, +1. So it can't be anything to do with charge, but it's something to do with charge density, which is related to size. The smaller the size of the ion, the higher the charge density is going to be. Smaller lithium ion means a better overlap between the lithium and the chlorine. The sodium's slightly bigger, so you can't get quite as good contact between the sodium and the chlorine. Potassium and chlorine, the potassium's bigger, so you get slightly worse contact here, and then for the cesium, because it's even biggest, there is much less contact. So it's charge density. The higher the charge density, the higher the amount of energy that comes out is going to be. All right, and that's why, as lithium plus has the highest charge density here, chlorine, of course, is constant all the way through. Lithium's got the highest charge density, highest charge density, lithium plus. Cesium plus, because it's the biggest and still has a +1 charge, has the lowest charge density. Therefore, the amount of energy that comes out is less. It's still a good amount of energy, but it's less. We're talking about a trend here. So that's a little bit about lattice energy. So, and like I said, you can see it's related to size, because the size of the metals here in group 1 increase going down the table. We've seen that before. Now let's look at a different example though. Sodium fluoride versus calcium oxide. The sizes of these, the size of sodium and calcium is not hugely different. The size of fluoride and oxide is also not hugely different, and you can tell that by looking at the distance between their nuclei. It's about the same. Because that distance is about the same, that means the radius of each ion is about the same too. Which would lead you to believe that these lattice energies then should be about the same. But oh boy, you can see, wow, there is a big difference here. These are not the same at all. Why is it that I get so much more energy out when I form calcium oxide than I do when I form sodium fluoride? Well, it comes back to the issue of charge density again. So let's just write this out. Charge density. Alright. If I have a ball, let's say that size, with a charge of +1, and I have a ball about the same size with a charge of 2+, per unit volume I have twice the charge here than I do here. That means twice the attraction for whatever this is attracted to. Therefore, better contact. And it's exactly the same for the anions as well. If I have something that's 1- and something of similar size that's 2-, I'm going to have a better attraction to this than I am to this, because there's a higher charge density. Therefore, a stronger attraction. So what that means, the attraction between these two is going to be pretty strong, but between these two it's going to be stronger because the charge density is higher in each case. If the attraction is higher, that means a more stable situation when they come into contact with each other, therefore more energy comes out. And so that's why we get so much more energy released. So you can see that lattice energy has a lot to do with the charge on the ion. So after we have done, you can see it's got a lot to do with the charge on the ion. All right. So really, what that means is the higher the charge, or really the higher the charge density, then the stronger the attraction is going to be, and the more exothermic the lattice energy is going to be, the higher the magnitude is going to be. All right. So with that in mind, let's go through a couple of examples. It says, arrange the following ionic compounds from lowest to highest lattice energy. Therefore, the smallest lattice energy first, the highest lattice energy at the end. All right, last, I should say. So, lithium bromide, potassium iodide, calcium oxide. All right, let's just take a look at these. We need to look at charge density. So we know for lithium bromide, it's Li plus, Br minus. Potassium iodide is K plus, I minus. Calcium oxide is Ca2 plus, O2 minus. All right, now this is where we need to look at the periodic table. If we look at, say, lithium, potassium, and calcium, well, the thing that we'll notice is the fact that the sizes are not hugely different, but their charges are. Calcium has a much higher charge, has twice the charge of potassium and lithium. Bromide, iodide, and oxygen, well, bromide and iodide are much larger than oxygen, plus oxygen's got the highest charge. So therefore, out of the anions, which anion has the highest charge density? Well, that's oxygen. And out of the cations, which cation has the highest charge density? Well, that's calcium. So which one of these three compounds has the highest lattice energy? Well, it's the one where the atoms have the highest charge density. So that is calcium oxide. So we're going to put calcium oxide highest here. Now we've got to figure it out between lithium and bromine, or between lithium bromide and potassium iodide. If we look at lithium and potassium, you will notice that lithium is considerably smaller than potassium. So out of those two, lithium's going to have the higher charge density, even though the charges are the same, lithium's smaller. When we look at bromide and iodide, bromide, although it's large, is smaller than iodide. So therefore, bromide is going to have the smallest charge density out of those two. So therefore, lithium bromide comes second, and the one with the lowest lattice energy, although it's still going to be exothermic, it's going to be lower than the others, is potassium iodide. So that is our order. Now let's do the same thing for these five. It's a little bit more complicated, but the idea is basically the same. Again, it's charge density we're looking at. We're looking for charges. So we have aluminum, magnesium, potassium, sodium. All right. The thing that is going to be kind of a deal breaker here is the fact that aluminum is 3 plus. Magnesium is 2 plus. Potassium is plus. And sodium is plus as well. Notice the anions in each case are exactly the same, apart from oxygen. All right, but we can do all these chlorines here. So we know, because the chlorines are all the same, it's going to be the metals that we're going to use to determine what is happening. So if you look at the periodic table, you'll see Mg2 plus has a very similar size to Al3 plus, has a very similar size to Na plus, and K plus is one period lower, so it's a little bit bigger. So out of those four metals, which one would have the highest charge density? Well, it's the one with the highest charge. In this case, it's aluminum. So I'm going to put AlCl3 here, because I know that AlCl3 is going to have a higher charge density than magnesium chloride, simply because Aluminum's got a +3 charge, magnesium's got a +2 charge. It doesn't matter about the number of chlorines, because each of them are Cl-. What matters is the metal here. But what about the sodium chloride and potassium chloride? The chlorides are the same again. The difference here is sodium and potassium. Alright? Which one's bigger? Well, potassium's bigger. Therefore, the one with the higher charge density is sodium, the smaller one. Right? Therefore, the one with the lowest lattice energy is going to be the biggest atom, which is potassium. So therefore, our KCl is going to come first. Now notice I haven't done anything about the Al2O3 yet. Although you can probably figure it out where it's going to go based on the fact I don't have any spots here. Aluminum 3+, aluminum 3+. In both of those cases we can't make any differentiation about the aluminum. Chlorine and oxygen, though, we can make a differentiation about. Chlorine is Cl-. Oxygen is O2-. There is not a huge differential in size here between these, but there is in the charge. So if we have a charge of 2- and a charge of 3+, we're going to have a better attraction between these versus these, which is 3+ and 1+. So again, it's the charge that's particularly important. So therefore, the salt with the highest lattice energy is going to be aluminum oxide. All right. Now, one more thing before we finish here. Let's see how this applies to things outside of chemistry. Knowing the melting points of things for particular industrial processes is really important. And to be able to predict those is equally important. So based on lattice energy theory, which of these would be expected to have the highest melting point? Sodium chloride, magnesium chloride, or aluminium chloride? Well, so we are comparing aluminium chloride, sodium chloride, and magnesium chloride. Well, if we think about it, we know AlCl3, aluminium chloride, has the highest lattice energy. Therefore, the strongest attraction between the two ions, because of the largest amount of energy given out when they form, when AlCl3 forms. That's higher than magnesium chloride, which is higher than sodium chloride. So if this has the highest lattice energy, does it make sense that that means those ions are held together the strongest? And if that's the case, what does that say about the melting point? Well, it says what I imagine you think it would mean. If these ions are held together the strongest, this is going to have the highest melting point. Then this, and then this. So you can see lattice energy has a direct correlation to melting point. Alright, so that's it about lattice energy. Thank you very much.